Hello everyone, welcome to the video. So in this video, I'm going to show you how to design an audio amplifier circuit. So we'll see this as three sections. In the first section, I will show you how to simulate the audio amplifier circuit on the LTspice simulator. In the second section, we will see a practical demonstration on how to implement the circuit on a breadboard and verify the results on a speaker. And in the last section, we will see how to perform the design of the circuit by doing calculations on paper. So let's start with the simulation. So you can see here that I have connected the circuit of the amplifier. So we are providing a voltage of 9 volt as power supply, and then the input signal will be around 500 millivolts audio frequency. So we can initially I have defined it to be 20 hertz, and it can go to a maximum of 20 kilohertz. So this is modeled as a sine wave source. Then the input is coupled to the base of the common emitter stage of the amplifier, which is then the output of the common emitter stage is coupled to an emitter follower, and finally we have a class AB driver. So the output of the class AB driver is connected to the speaker, which is modeled as a 8 ohm resistance. So we are going to perform a transient analysis for 10 seconds. Let's simulate the circuit now. So let's plot voltage across the speaker resistance. And we are observing that the speaker is the voltage across the speaker is around 1 volt amplitude or 2 volts peak to peak. Let's see the voltage across the common emitter amplifier stage. So we are seeing that it is around 4.8 volt uh, peak to peak. Let's now plot the input waveform. So this comes to around 1 volt peak to peak. This signal as we have provided using the source. So let me show you a magnified version of this. So now you can see all the signals here. We can observe that the phase of the output waveforms are shifted by 180 degree from the input waveform. This is due to the usage of CE amplifier. So let's now proceed to the practical demonstration. So now we are going to see a demonstration of an audio amplifier circuit. And so here this circuit is made up of 4 transistors. The power supply is a 9 volt battery that you see here. And the input signal is connected from my mobile phone through an aux cable. And we have, as I said, we have 4 transistors here. So the first transistor is a BC547 transistor, which is connected in the common emitter mode. So this transistor provides a voltage gain of around 5, and the output of this transistor is coupled to another BC547 transistor, which acts as an emitter follower. So this is the gain of this transistor is unity, but it is used for matching the impedance to the output. Then the next stage is class AB driver, which consists of these 2 transistors. So this transistor is 2N2222 and the other one is 2N2907, which is a NP and PNP pair. And this entire pair is biased by using 2 diodes, 1N4 and 4,8 signal diodes. And the output from this stage is coupled to a speaker through a capacitor. So this speaker is a zero point 0.4 ohm, sorry, zero point 0.4 watt, 8 ohm speaker, and the overall gain that we get out of this amplifier is around 2. So the uh, gain is 2 because the class AB amplifier is actually attenuating the signal instead of uh, giving a gain. One important point to note here is that we have to connected two 5 ohm resistors to the emitter of the power transistors used here. So the use of this 5 ohm resistor is that when I initially connected the circuit, I didn't use these resistors. So this was causing the transistors to get heated up. This is due to thermal runaway, and we have included this resistor to reduce this effect of thermal runaway by a negative feedback effect. So this is the overall circuit. Now will see the result. Let's analyze the circuit of the audio amplifier. So this is the circuit, and the values that you see on the right are the specifications of the amplifier. So we have chosen a VCC of 9 volt, Vin of 1 volt peak to peak signal. The gain of the CE stage of the amplifier is 5, which is the gain provided by this part of the amplifier. And then the minimum frequency that we would be using is minimum audio frequency, which is 20 hertz. Then we have chosen a collector quiescent current of 10 milliamps. We want this to be low because we are using battery as a power source. So we want the current through the collector to be very less. Let's analyze how to design the CE stage of the amplifier. So step 1 is to set the quiescent point. So for setting this quiescent point, we are assuming that VE is equal to zero point 0.8 volts, which is actually 10% of the VCC, which is 9 volt. Then from VE, we are calculating RE. So RE is given by VE divided by IEQ. IEQ is actually the quiescent emitter current, and this set in the specification as 10 milliamp. So zero point 0.8 volt by 10 milliamp gives 80 ohms, and for to now to use standard resistors, we are choosing this to be 82 ohms. Then we get the collector resistor RC. So in order to get RC, we are calculating using the formula VCC minus VCQ divided by IC. VCQ here is actually chosen to be 5 volt because we want equal swing of the output waveform on both sides of the quiescent point. So hence we are choosing a midpoint. So RC is given by 9 minus 5 by 10 milliamp, which is equal to 400 ohms. And to choose standard value, we are choosing 390 ohms. Next is the base voltage. So in order to calculate VB at quiescent point, we are calculating VE plus the voltage across this forward bias diode VBE. So this is given by 0 0.8 volt plus 0.7 volt, and it is equal to 1.5 volt. So the current through the base at quiescent point is given by IBQ, which is equal to ICQ by beta. For B27B, B547B, I'm sorry, BC547 transistor, the beta is 200. And if we calculate 10 milliamp by 200, we get 550 microamps. This is the quiescent current that flows in through the base of the transistor. I auto is given by 10 times I BQ. Since we are choosing this value because for the stability of the circuit we are choosing 10 times of the base current, and this comes around 500 microamps. So from this we can calculate R2 as VB by IR2, which is 1.5 by 500 microamps, and it comes to around 3 kilo ohms. Finally, R1 is VR1 by IR1, which is 9 minus 1.5 by 550 microamps, and this value turns out to be 13 kilo ohms. So in step 2 of the C amplifier design, we need to set the AC voltage gain and impedance. In order to do this, first we are calculating the RE dash value, which is the internal emitter resistance. It is given by the thermal voltage divided by IEQ. The thermal voltage for any device is equal to 25 millivolts at room temperature. So 25 millivolts by 10 milliamp gives 2.5 ohms, which is the emitter internal resistance. So using this value, we need to calculate the collector, uh, the RE1 resistor value. So in order to calculate that, we are using the expression collector gain is equal to, I'm sorry, voltage gain is equal to RC by RE1 plus RE dash. So this implies phi is equal to a voltage gain of phi is equal to 390 by RE1 plus 2.5, and from this expression we get RE1 is equal to 75 ohm. RE2 is given by RE minus RE1, which is equal to 82 minus 75. 82 is the value of resistance that we total emitter resistance that we calculated in the previous step where we determine the quiescent point. So on calculating this, we get 7 ohms. So this type of RE1, RE2 division in the resistances is called emitter degeneration. So we need to do this in order to ensure the stability of the amplifier and to provide the right gain. So once we calculate RE1 and RE2, the next step is to calculate the AC input impedance Zin. In order to calculate Zin, first we are calculating ZB, or the impedance when looking at the circuit from the base of the transistor. So this is given by beta times RE1 plus RE dash. So beta for BC547 transistor is 200. So 200 times 75 plus 2.5 gives a resistance value of 15.5 kilo ohms. Finally, using this value, we are calculating Zin, which is given by the parallel combination of R1, R2, and ZB. So this is 13K in parallel with 3K, which in turn is in parallel with 15.5K. That gives a resistance value of 2 impedance value of 2.29 kilo ohm for the input impedance of the CE amplifier stage. In step 3, we are going to select the capacitor values for the CE amplifier. So in order to select the capacitors, we are first calculating the capacitive reactance for the emitter capacitor. So there is a thumb rule of choosing this reactance to be 1 by 10th of RE2. Since RE is 7 ohms, we are doing 1 by 10th of 7 ohms, and which gives 0.7 ohms. From this 0.7 ohms, we need to calculate the capacitance required to provide this capacitive reactance. So for that we use the formula 1 by omega c, or 1 by 2 pi fc, and for f we substitute the minimum frequency for the input signal, which is 20 hertz. So using that we get 1 by 2 pi into 20 into zero point 0.7, which gives a value of 11,368 microfarad, and to select standard values we are selecting a 10,000 microfarad capacitor. Next step is to determine the input capacitor at the signal input. So for that, we again use the thumb rule Zin by 10 to get 1/10 of the input impedance for the Cin reactance. So for using this Zin that we calculated from the previous step, that is step 2, we get 229 ohms as the result. Once again, we calculate C in from the formula 1 by omega C, which is equal to 1 by 2 pi times minimum frequency, which is 20 times 229. This gives a capacitance value of 34.8 microfarad. So, in order to choose realistic practical value, we are of the capacitor, we are using 47 microfarad. Having designed the CE amplifier stage, the next step is to design the CC buffer stage. So here again we have a BC547 transistor and the which is being DC coupled to the C stage. So we are choosing DC coupling here because we need not have a separate network for biasing the uh, common collector stage. So we are directly coupling the output of the C amplifier to the base of the CC stage. So in order to limit the current through the buffer stage, the base current, we need to have a coupling resistor. So in this design step, we need to calculate the value of the coupling resistor and the emitter resistor for the CC buffer. So the rationale behind choosing these resistors is to have a high input impedance and a low output impedance for this stage. So Zin of CC buffer should be high and Z out of CC buffer should be low. So this Zin is given by the formula beta times RL plus RE dash. So any CC buffer would try to provide a high input impedance because it is multiplying by the factor beta. So whatever be the output voltage, it will not load down the CE amplifier. And once again, Z out is calculated by using the formula RE in parallel with R source by beta. Here, R source is the output impedance of the CE stage. So, based on this rationale, we are choosing a coupling resistor value of 1 kilo ohm so that the input impedance is high and a RE value of 100 ohm so that the output impedance is low and it isn't too low so that we should also ensure that RE is not made too low so that it consumes too much power from the battery. So 100 ohm seems to be a good seems to offer a good trade-off between the two rationals, and we have chosen this particular value. The final step is the design of the class AB stage. The output of the CC buffer is directly coupled to the class AB stage. In this stage, we need to calculate the value of resistors R1, R2, R3, and R4. So, in a class AB amplifier, one of the transistors conducts for one half cycle of the output waveform, and the other transistor conducts for the other half cycle of the output waveform. So, for doing this, for this purpose, we are connecting two diodes, 1 and 4 and 48 signal diodes. These have a voltage of 0.7 volts across them. And in order to choose the value of R1 and R2, initially I went for simulating a 10 kilo ohm resistor for these values, for these resistors. But I found that the output voltage was clipping, and so it is necessary to establish a proper base current, quiescent base current, to avoid clipping. So for that, I observed that when we reduce the value of the resistance, the clipping is avoided. So I found that 1 kilo ohm is a suitable value for this setting up the quiescent base current. For R3 and R4, I have chosen 5 ohms because these resistors are used to ensure that thermal runaway is avoided by a negative feedback effect. We can even go for smaller values like less than 1 ohm, and the minimum value that we can choose is around zero point 0.1 ohm based on some design guidelines. The output is coupled to the speaker through a 1000 microfarad capacitor. This 1000 microfarad capacitor blocks the DC voltage completely and lets in only AC to pass to the speaker. So the 1000 microfarad value is chosen because we want to let in at least 20 hertz frequency waveform. I have one question for you. In this amplifier, we are using a power source of 9 volt. So if we have a mobile phone, the battery voltage source is around 3.3 volts or less than that. So with that 3.3 volts, how is the mobile phone able to play music with such high volume? What is the kind of amplifier being used? Or take the example of a smart speaker. What goes into the smart speaker amplifier that makes it play it with such a loud volume? Can you guess what kind of amplifier is being used in these circuits? Please let me know in the comments. And finally, I would like to thank Google Gemini tool for helping me to design this circuit. Actually, all credits should go to Google Gemini because in all my design iterations, I prompted Google Gemini to provide the resistors and capacitor values. So it was completely responsible for designing this entire circuit. Thank you for watching the video.